Yes, so Simon Helling, it's a future PhD candidate in Germany. So, and he has done his master at Erlangen-Nuremberg, while Alessio Gravina is a PhD student at Pisa with Pachu and Gallicchio. Yes, and I suppose you both, yes, studied computer science. So yes, so please, if you want to go ahead.
Yes, of course. Thank you very much for the invitation. We are very happy to present our latest work we did over the last month. And it's all about using physics concepts like Hamiltonians to view graph neural networks as a dynamical system, as done in the last recent works. And then we were able to derive some powerful theoretical statements, and we did experiments on long-range data sets. So we tried to increase the distance these models can propagate information. And as I don't know how you are confident in this field, we provided some background, so very basic introductions, and then we will touch on our model we proposed. And Alessio is going to talk about the experimental validation part. So that's the outline. I hope my connection and sound is good so far. Let's dive into it. So the background, we are doing machine learning on graphs. And I think from the names in the participants list, I assume at least some of you are familiar with the concept of having a graph like nodes of customers and linking them together with a relation of edges. And then we maybe want to recommend customers to products as a use case. And usually we do this by embedding this structured data into a d-dimensional vector space, and then we can do classical machine learning there in this space on the right side. And then we need a notion of similarity distance to get these, okay, now the customer and the product are very close, maybe they relate together. So our manifold should be very informed about the structure and the content of the nodes. So we assume some information at each node and maybe some information on the edge. And then we need to aggregate all this information to get a very informative embedding for the downstream task. And here today, we're not very caring about the application side because we're doing only benchmark data sets later on. But you can imagine in material discovery, the usual applications out there on proteins, for example. So this is where we are in this space. Feel free to chat if I'm too fast or if any questions arise, but I guess we do a Q&A at the end. Okay, so the main framework in the last years that proposed to touch this problem of embedding some graph data into d-dimensional vector space is based on the message passing neural network framework. So we get a graph, then we have a already encoding of the information into a latent space. Then we have this deep graph network, which is aggregating the graph information, the adjacency information and the edges. And then we get an informed graph. And this graph can be decoded in a lot of various ways. So we can do node level tasks, we can do graph level tasks. So there are pooling strategies in this decoding module. And then we do end-to-end training of all these components with a loss. And this is the usual downstream task loss. So we're having task-specific embeddings here and not general purpose embeddings. That's maybe a very important point. And the first equation is the most general way how to formalize this. So basically each node U gets some initial information, And then we are aggregating the messages from the neighbors. And the messages is just, okay, I'm your neighbor and I'm in state X. Maybe you are interested in this state where I am. And then you aggregate all the information from your neighbors and you somehow need to internally update your state. So this is a very state-based perspective and a very discrete perspective because we do it layer-wise. And a layer here is not like a deep graph network, a deep learning model where the layer is just one more hidden layer. But here the layers is the number of aggregations we do in the graph. And maybe a more intuitive equation, which could be really implemented in this way, is that we have a MLP, so a weight matrix computing the message of the neighbors. And the aggregation function is just an unnormalized sum here. And then our update is nonlinearity, for example, 10H, with our self message. So we're having some form of self loops here. And then we combine these two into our new discrete next state. And while training, we need to hyper evaluate basically how many layers we want to do here. And then you have a terminal layer. So one last layer, which is determining the last embedding of the node. And this is passed through the decoder to predict the classification or regression problem. And this is on a node perspective. So each small x is a node and a big X is a complete graph matrix. So here we're having row-wise arranged syntax. And then you can transform these equations back to matrix multiplications. And then we have PyTorch geometric, for example, as a framework where you can implement these equations. And the last equation is just an example of doing a residual connection here on your previous state with the updated neighborhood information from the adjacency matrix. This is A. And maybe you want to interpolate with your initial state. Maybe you want to interpolate with your previous state. So there are multiple different ways how you can approach this. But bottom line, you do layer-wise aggregations of information. Okay, so that's the old work, basically. And in the last years, people started to view this discrete system as a continuous way because we can describe this interaction also in a continuous time. And then you have a dynamical system which is coupled on the graph. And this introduces graph-coupled neural ODEs. So basically, each node is a neural ODE, and then you inform all the neural ODEs by the adjacency information. And this is captured here in the phi function. So each state for each node U is informed by the others in a continuous way. And then you have your basic MLP syntax with the bias you can adjust as a parameter by the gradients. And having a continuous perspective and a discrete perspective is bringing a lot of opportunities here because we have old tools how to analyze dynamical systems from the dynamical system theory. And then we can bridge to the discrete world where we are right now. And we want to implement the discrete world as a message passing. So that's basically related work. And for example, the work from Alessio studied how to adjust the weights to arrange the continuous dynamic to have favorable properties. And as we are in a dynamical system, we can also study attracting points in the system or how is the flow in the system. So all the language from dynamic systems is introduced by this bridge of viewing the continuous and discrete dynamics here. And most importantly, we are interested in long-range interactions. So what if the problem radius of your graph is more than 30 hops far away? So you need to aggregate 30 layers of messages, because this is one solution to underreaching. So here we want to inform the source node with the target node, or the other way around. And we need to propagate at least 5 times the information from source to target. If our model is not deep enough, then the information cannot reach this. So we need at least 5 layers, or 30 or 50. But if you do this naively, in the last years, people started to observe some unfavorable effects, let's call it this way. And these unfavorable effects are over-squashing and over-smoothing. Just as a background, over-squashing is basically that you have a finite dimensional state and you squash exponentially many messages in these finite dimensional state. And then you lose basically information, you lose track of the information. And then over-smoothing is the effect that you're aggregating, and then the Dirichlet energy in the features is diverging, is converging to 0 very, very quickly, exponentially actually. And then you have an uninformative state of the global graph. So that's very unfavorable, because the final state is the start for the decoding layer, so the downstream task. And if you have a non-differentiable state at the end, then each node looks like the same and you cannot do any downstream classification regression whatsoever. Okay, so that's a problem set up. And we arranged this work with a Hamiltonian setup. So the Hamiltonian in physics is very basic and found in a lot of different areas. So for example, in astronomy, where you want to do the n-body problem prediction. So n bodies are interacting with forces, and you set up this system by starting with an equation, the Hamiltonian equation, capturing the energy of the state, the complete state, the global state of all the nodes. So here, for example, kinetic and potential energy in T and U. And then you have this P and Q part of the state. And P and Q is just a split of the entire node. And P is the momenta, the acceleration part, and Q is the position in space, let's call it this way. And if you do it like that, you have your global energy and a very specific algebraic function for your energy potential. And then you apply the dynamics of Hamiltonian. So this line is defining how the bodies are moving and interacting with each other by partial equations. And this can be formalized in a global vector y without using P and Q. This is just a rewriting, a merging of these two equations here, and by introducing this skew symmetric matrix J, which is just identities in the right spot. So to split up the P and Q. But now you're having a global state vector y without handling the P and Q separately. And the favorable properties of Hamiltonians is that they conserve the energy in the state. So the state is not attracting to a global attracting point. So you don't have a differentiable information state, but you have infinite future states which are different, because the energy where you started will be constant over time. So you can integrate these systems arbitrarily long on paper, but we are doing numerical computations. So that's the basic setup. And we are inspired from this n-body problem setup basically, but we are using a different Hamiltonian function. And this brings us to the port-Hamiltonian framework we proposed in our work. And basically we set up this global y for each vector xu, the P and Q part. And then we set up this energy function, which is very arbitrary, but we aim for algebraic formulations to end up as a message passing framework. So we took the anti-derivative of the nonlinearity, because we're doing derivatives in the dynamics, to end up with the real nonlinearity. And then we set up this graph coupling classical framework for neural ODEs. But we sum over all the nodes in our system or in the batch, which is a global approach. So that's the first insight. If your system needs to be constant in energy, you cannot start locally, but you need to start globally. And then you apply the Hamiltonian equations. So you basically derive this H function, the Hamiltonian function, with respect to Y. And then you get local equations, because you look at the components which correspond to the node vector. And this is just on paper so far. And we have this favorable property of having a constant Hamiltonian energy function. So its derivative with respect to time is 0 everywhere, if you do it the purely Hamiltonian way. And if you do it on paper, how the gradient looks like, you get this equation. So basically, you get a residual update as we saw it before in the related work. So far the same, but then you get this, let's call it energy correction, because you need to account for the neighbors of the neighbors. And what am I meaning with this? Because you look at the neighborhood of your nodes, and then you aggregate the informations of the nodes of your neighbors here in this term. But you're updating, so it's basically a 2-hop view. And you have this and this is continuous world, but we are doing discrete computations. And if you're dealing with Hamiltonians, you need discrete integrations. So symplectic integrations, which conserve the measure, so which conserve the energy. And it's a little bit more complicated than forward Euler integration, but not very complicated. You just need some structure assumptions so that the Hamiltonian becomes separable. And if the Hamiltonian is separable, your system becomes explicit. Because if your system is implicit in an integration, then you need to solve linear equations in each update step, and you don't want to do this. Okay. So that's a continuous, conservative, purely Hamiltonian approach for a graph neural network. But what if the purely conservative dynamics are not sufficient for your downstream task? Then you maybe want to lose information, or you want to gain, you want to position the nodes on a different circle. Then you need to be dissipative. But you don't want to be fully dissipative, and you don't want to decide on this beforehand. You want to learn this end to end. And a very good framework for this is the port-Hamiltonian dynamics. So it's building up on the purely conservative, but deviating by internal dampening, for example, so friction in the system, and by external forcing. And here you have high flexibility in designing these components. We end up with this simple related work framework for port-Hamiltonians just as a startup. But you can really engineer here a lot of things for these dampening and external forces. And how do we determine this D and F? It's a MLP, or it's a one-layer graph neural network, again, coupling. It is time dependent, or it could be not time dependent. So you really have high flexibility here. And then you do the end-to-end framework, and you get out how much do I need really to deviate from the conservative trajectories to get the most out of the embedding for the downstream task. And that's the big picture. So here you have your energy correction, which is phi star, and you have this split up in P and Q. And then you can inject the internal dampening and external forcing parts to deviate from the conservative setup. And this is now discrete world. So you really can do it as a message passing framework layer by layer. And then the coupling is arbitrary. So you can transform already existing message passing networks into its energy preserving version or in its port-Hamiltonian deviating version very easily. So you can do GCN, you can do GATT, you can do GraphCon, everything can be plugged in this PHY. And we observed how to modify this message passing in order to obtain a global energy conserving state. So that's the framework. And now that we have a continuous world, we can do theoretical analysis on the continuous world. For example, our eigenvalues are purely imaginary, which is the most important statement for doing long-range information, because then your dynamics are stable and non-dissipative. We knew that already, but now we have it also linked to this field. And you can say something about the nonlinear dynamics directly in our framework, because this is a Jacobian statement, so a truncated Taylor series statement, but we are doing also divergence statement on the nonlinear dynamics directly. And it's in fact a non-divergence. It's a divergence-free nonlinear dynamic. So we're having no explosion of energy in the conservative setting, and we're having no dissipative component here in the purely Hamiltonian setup. We have a divergence-free dynamic here directly, which is a strong statement. And we are interpreting this as a long-range property because our dynamics possess these two statements. So that's for stability side, but we can also say something about the sensitivity because we're having the Hamiltonian framework. So we know that, for example, our gradients on the self node cannot vanish. So we're having it bounded from one. So no matter how far you integrate, so t is the terminal time, you will always know where you started. Or the past always influences the future, always, in the purely conservative setup, which is a very strong statement in the continuous and in the discrete statement, because now you can really integrate arbitrarily far in the future. But what about the upper bound for the gradient on the self node? We get an exponential explosion because you need to remember where you started. You really need to focus on your past. So you get an exponential in terminal type t. So the more you integrate, the more you need to focus on the past, which is a trade-off here. And in a numerical example, you get a log linear behavior. So that's a log scale, and that's a linear behavior roughly, which is basically an exponential behavior. So you get the last state of your embedding procedure, which is passed in the downstream, and you want to know how the previous layers influence this last state. That's the statement. So that's the initial layer, and the initial layer influenced the most how the last state looked like, which is also very informative here. So we really know how the dynamics behave in our system if you do the conservative part. If you do the port-Hamiltonian, you lose all these nice statements because you deviate. For example, this statement won't be possible with away from zero with a port-Hamiltonian, because you can lose information here. That's also very interesting. And now we're going into the experiments, and Alessio will share his screen.
So okay, now we move on with with evaluation of our port-Hamiltonian deep graph network. And so in order to assess the efficacy in preserving long-range information between nodes, we designed the graph transfer task and employed other two benchmarks, which are the graph property prediction and the long-range graph benchmark. So in the first experiment, which is the graph transfer task, the idea is that we want to propagate a label from a source to a target node located far away in the graph. And specifically, we initialize the source and the target nodes with label 1 and 0 respectively. And then we randomly initialize intermediate nodes with values between 0 and 0.5. And note that by randomly initializing these intermediate nodes, we are increasing the complexity of the task because we are injecting noise in the task. And we consider increasing distances between targets and source nodes. And in particular, we consider distances of 3, 5, 10, and 50 ops away. So, of course, we are requiring incrementally higher efficacy in propagating long-range information. And we consider three main graph topologies, which are the line graph, the ring graph, and the crossed ring graph. And to keep the task challenging, instead of having a binary classification task, we consider the mean square error as a metric. And here in this plot, we can see the performance of classical message passing neural networks when propagating the information across a line graph. On the x-axis, we have the distance, so the number of hops needed to effectively deliver the information to the target node. And on the y-axis, we have the metric. And since we use the mean square error, lower values corresponds to better performance. And as you can see, the trend shows that to an increased distance between the source and the target nodes correspond worse performance. And this is in line with the literature. Indeed, this kind of architecture are extremely effective in learning and propagating local information. So information that is within 3, 5 ops away, while they perform very bad as the distance increase. So as we stack multiple DGN layers. And this is due mainly to over squashing phenomena and the fact that these kind of models are not able to perform long-range propagation, because this phenomenon creates a dissipative effect, as we discussed before, on the resulting deep graph network. But for example, if we introduce a baseline like ADGN that Simon was referring before, that has a non-dissipative behavior, this trend is mitigated as expected. But with our, thanks to our purely conservative behavior, our Hamiltonian deep graph network can further improve the long-range capability obtained by ADGN. And overall, if we consider the three topologies, we have that the message passing neural networks do not effectively propagate the information across the long ranges, as their performance decreases when k increases. And while differently, our Hamiltonian deep graph network achieves low errors even at higher distances. And it is on average better than ADGN. And so these empirically support our claim to achieve long-range capabilities while introducing a new architectural bias. So then we move to the graph property prediction benchmark, which was first introduced by Gravina et al. In ICLR 2023. And here the aim is to predict three graph properties, which are the graph diameter, which is the shortest path between the two more distant nodes. So for example, here in this simple graph, the diameter is 2, since it is the longest among all the shortest paths. And then the second property that we want to predict is a single source shortest path. So here we randomly select one source node, and then we compute the shortest path with all the other nodes. And then the last property that we predict is the node eccentricity that corresponds to the length of the longest shortest path starting at each node. And so we predict for each node this metric. So to summarize, the first task is a graph level task, while the others are node level tasks. So here in this table, we report the results on this benchmark, and specifically we report the logarithm of the mean square error. And overall, both our Hamiltonian deep graph network and its unconstrained version, so the port-Hamiltonian version, show strong improvements with respect to baselines, achieving new state-of-the-art performances in all the tasks. And in particular, our results shows that the purely conservative Hamiltonian deep graph network has an average log mean square error that is 0.33 lower than the baselines. But although our purely conservative model shows improved performance with respect to all the baselines, it appears that relaxing such bias is more beneficial overall. And this leads to an even greater improvements in long-range information propagation, because indeed this gap is pushed to 0.81 when the full port-Hamiltonian bias is employed. And if we consider only as baselines state-of-the-art message passing neural network, our port-Hamiltonian deep graph network improved the performance by almost 2 points in the metric. Our intuition regarding the improved performance of the port-Hamiltonian version with respect to the pure Hamiltonian deep graph network is that such tasks, in this task, we do not require a purely conservative behavior, since nodes need to count distances while exchanging more messages with other nodes. So the energy may not be constant during the resolution of this task. And so this benefits the non-conservative behavior introduced by the port-Hamiltonian deep graph network. So as for the graph transfer task, even these results demonstrate that our framework can achieve state-of-the-art performance when modeling dynamics capable of long-range propagation. And lastly, we assess the performance of our method on the well-known long-range graph benchmark, focusing on the peptide func and peptide struct tasks, which are two real-world biological tasks where graphs correspond to peptide molecules. And peptides are short chains of amino acids that are abundant in nature, and they serve in many important biological functions. And for example, here in the picture, we have the 3D visualization of a peptide and the corresponding molecular graph. So the peptide func is a multi-label graph classification task with the aim of predicting the peptide function. And for example, here we ask if the peptide has antiviral properties or antibacterial properties. On the other side, the peptide struct is a multidimensional graph regression task whose objective is to predict the structural properties of the peptide, like the length, the inertia mass, the sphericity, and so on. And here we report the results on the long-range graph benchmark. First of all, we know that the message passing neural networks shows competitive performance, but they employ both positional and structural encoding, which help to incorporate more global information. So more long-range information. And overall, the majority of the baselines employ this kind of encodings. While our results, with our methods, we don't use any of these encodings, and the results shows that both our Hamiltonian and port-Hamiltonian deep graph networks are capable of outperforming classical message passing neural networks, graph transformers, most of the multi-hop deep graph network, which perform rewiring, and recent differential equation inspired deep graph network, which in this case represent a direct competitor to our method, since even our Hamiltonian framework is inside this domain. And notably, as I was saying before, our framework shows a great benefit in propagating the long-range information and achieves state-of-the-art performance without requiring any additional strategy, like global positional encoding, global attention mechanism, as in transformers, or rewiring techniques that overall increase the complexity of the method. So even these results reaffirm the effectiveness of our method. So coming to the conclusion of this talk, here we have presented our port-Hamiltonian deep graph network, which is a general framework that gauges the equilibrium between non-dissipative long-range propagation and non-conservative behavior, while seamlessly incorporating the most suitable neighborhood aggregation function. And so thanks to such general formulation, our framework can be used to reinterpret and extend any classical deep graph network through the lens of port-Hamiltonian systems. And so they allow to inherit this non-dissipative behavior. And we theoretically proved that when the pure Hamiltonian dynamic is employed, our framework allows for long-range propagation in the message passing flow, since the node states retain their past. And to demonstrate the benefit of our method, we conducted several experiments. And the results show that our method outperforms state-of-the-art models, and the inclusion of data-driven forces that deviate from this purely conservative behavior is often the key to maximize the efficacy of the approach on tasks that require long-range propagation. So here are just a few references that we cited during the talk. Thank you for your attention.